All right, this is a final exam review for Chapter 1 and 2. I don't have anything for the appendix chapter. Some of the things on the clicker quiz that you get will have some appendix solving problems that you do need to be able to do as well. You can look at your notes for the appendix chapter, the test, but there will not be a video review for the appendix chapter, which is pretty much just solving equations, or different types of equations and different things. But make sure you look at that appendix test as well, because that could be used throughout. But we'll see how this goes. This is the Chapter 1 and 2. I'm just going to go through the learning target sheet, all of this sheet, and as I do, other chapters are available on my website in the folders, or you should have copies of these that you got. I'm going to go very fast through some of these things, which I hope to, but maybe it'll be slow. And you can go back and look at them. All these problems over here on the side, you know, if you need more help in a section, you can go back and look in the book at those problems, or you can look at your test and look for problems like that. So hopefully this will work out. All right, the first section, 1.3, is on circles. Just to remember circles, the standard form of a circle, I'm just going to give you a circle actually. If I gave you a circle of, or an equation that said x plus 3 squared plus y minus 2 squared equals, let's say, 25, you need to be able to tell me the center and the radius. If it's in this form, this is the right form. If it's in this form, the center would be at -3, positive 2, and the radius, this is always r squared over here, so the radius would be 5. So if that's not a perfect root, then the radius will be some sort of square root, but the center would be at -3, 2, the radius is 5 if it's in that form. If it's not in that form, and if I give you the graph, you should be able to write it in that form. You should be able to do that from that equation that I just gave you. If you need to complete the square, if it's not in the right form, that completing the square process that we've done all year, maybe you want to go back and do one of these problems from this section to see if you remember how to complete the square, because maybe it's not in this nice form like this. This section here, write equations of circles given different information, is what if I gave you the endpoints of the diameter that's on the quizzes and stuff like that. To do that, you would need to know the distance formula and the midpoint formula, which is from a separate section. So just to really, maybe this goes on your review. You know, your one review sheet that you're making for the final exam, you know, I would put an example of a circle to make sure I remember that it's always in that form. Same thing with the distance formula, just to have it fresh for me. The distance formula is a square root of, it doesn't really matter which way you go, but x2 minus x1 squared plus y2 minus y1 squared. And you can be writing these down on your review sheet right now as well. I would start writing things down as you go through this video. That's the distance between any 2 points, and then the midpoint formula is x1 plus x2 divided by 2, comma y1 plus y2 divided by 2. And it's a coordinate. So make sure you have those ready, and that will help you do this section here, where if I give you like the center and a point on it, you have to figure things out. Main thing to know about circles is, you know, how to find the center and the radius, and then be able to complete the square. If you need to do any problems from that section, then you can do those. Let's move on to the next one. Evaluating functions at specific values. This is something that you should all be able to do. If I say f of x equals, f of x equals 3x plus 5, and I say find f of 2, you just need to plug 2 wherever you see an x. So f of 2 would end up being 11. So that's evaluating a function as specific. Determine if it is a function given the equation. This is something that I don't know if you remember. So how do we determine if something's a function just given the equation? We talked about that section right there where y can't be squared. We don't want y squareds. If you ever have a y squared, then it's not a function. And I shouldn't even say y squared. It could be y to any even power. So if you ever see something with a y squared in it, it's not a function. And if you graph something, like if we graphed x equals y squared, you can't graph this on your calculator, but if you graph x equals y squared, it would look like this. And we also know that's not a function because it doesn't pass the vertical line test. So that's not a function there. So anything with an y squared in it is not a function. If you want to go check some of those problems, that's good to do. Find the domain. Given the equation, we've been doing this all year long. There's two things that blow up a domain. The bottom of a fraction cannot equal 0, and the inside of a square root can't be negative. I think I have some problems to look at for that, so I'll go see if I can find one here. Here's one from a past quiz. This is the 132.1 2.6 quiz. Let's see if I can minimize this. So here it is talking about the domain. What is the domain of f of x? Well, there is no square root, there is no anything, so the domain of f of x is negative infinity to infinity. What is the domain of g of x? Well, here's a square root problem. So domain, one of the things that blows up a function is the inside of a root. So what would we do here? If we take that inside of that root, 12 minus x, and say it has to be greater than or equal to 0. Now it actually can be 0 in there, it just can't be negative, and then we just solve this. If we solve this problem, if I just move the x over, I get 12 is greater than or equal to x, which really means that x has to be less than or equal to 12. So all the numbers less than or equal to 12 will work. In interval notation, that would be negative infinity to 12. Just a quick review of interval notation as well. Parentheses on infinity always, and 12 would have a bracket because it is included. The domain of h of x, the only thing that blows up h of x is when the bottom equals 0. So this is everything but negative 2. This would be easier to write in set notations, all the values x such that x cannot equal negative 2. We could also write that in interval notation, but it'd be easier to write that in set notation. Make sure you know what set notation is and what interval notation is. That's a good little side thing for it. Ranges, and that was over there also. We cannot find the range without our calculator, or we didn't at this point in time. So to find a range, we would look at it. So it says, what is the range of f of x? Remember, range is up or down. So when you graph it on your calculator, you're just looking for the lowest it can go to the highest it can go. So if you need to know that, write those things down. The range of g of x, the same thing, we would graph it. And if we graph g of x on our calculator, it would look something like this. So the range is the lowest that goes to the highest it goes. So the lowest it goes is 0, and the highest it would ever get to would be infinity. So its range would be 0 to infinity. Write an example of something that's not a function. That's like anything with a y squared in it. So if we say y squared equals x, that's not a function. Just anything with a y squared in it is not a function. I'm getting ahead of myself now. If I want to get back to the learning target sheet, sorry. So do all of the above given a graph. You have to be able to, if I give you a graph, tell me the domain of it, the range of it, determine if it's a function, all that stuff, x and y intercepts you should be able to do. So there's section 2.1. 2.6, main thing here is composite functions. Know what a composite function is. So if I go back to that quiz that we were just looking at, we can just kind of go through all of these things, but it's pretty much on this quiz here. So here's adding two functions. Well, that's, you just find f of 3 and g of 3 and add them. Now remember f and g, if I can kind of scroll, there's f and g. So we would just, this is really f of 3 plus g of 3. You just do them separate. So nothing really difficult there. You find f of 3 by plugging 3 into the f function. Find g of 3 by plugging 3 into the g function. Add those two answers up. No big deal. But this is a composite function. Okay, this is read g of f of 3. Now just to remember, where does the 3 go first? The 3 goes into the second one written first. So the 3 would go into the f function first. So if we plug 3 into this f function up here, we get 9 minus 3, which is 6. So f of 3, and another way this could be written is g of f of 3. You don't have to have the circle there. That's also a composite function like that. So we just did f of 3, and we got 6. But now we have to find g of 6. So really we plugged the 3 into the f function, got an answer of 6. We now take the answer 6, plug it into the g function, which is right in there, and 12 minus 6 is 6, so it ends up being the square root of 6 is the final answer. And that is a composite function. If those were reversed, if that said f of g of 3, then the 3 would go into the g first and then the f. This is f of g of x. Same type of thing. You just plug x into g, which it already is. There it is, square root of 12 minus x, and then plug that into f. And if we plug that into f, you'd end up squaring the root 12 minus x. So you just end up with 12 minus x, and then minus 3. So remember the x. So you end up getting, I'll write it down here, square root of 12 minus x squared, and then minus 3. Well, that would just be 12 minus x minus 3. which is 9 minus x. And that's f of g of x. So those are composite functions. If you need more help on those, you can go do those. Oh, find the domain of a composite function. One of my favorites, and that's also on that learning target there. To find the domain of a composite function, it must work in the first one. So it's got to work in g of x, because that's the first thing that's going to get done. So I run up to g of x. The restrictions on g of x, we already found the domain of g of x, and this was the domain of g of x. So that's starting the domain right there, negative infinity to 12. So it has to work in the first function, and it has to work in the final function. Well, here's the final function. We already found f of g of x. It was right there. Nothing will blow that up. So it has to be the intersection of, this is negative infinity to infinity as a domain, because nothing will blow it up, and the other domain of g of x, which is negative infinity to 12. So the domain of the composite function just ends up being negative infinity to 12, because that's the intersection of those two. Remember, the domain of this one I said was negative infinity to infinity. The main thing to remember to find the domain of a composite function is it has to work in the first function and it has to work in the final function. And then you find the intersection of those two domains. So what works in both? This is going backwards, and you can look at those as well. You know, if I give you the pieces, can you write the original function? Some good practice, some good things in your notes on that too. So if you need more help with that, I would take a look at those. All right, we got all the way through there. Now we're looking at lines. Find the slope of a line. This is like basic algebra, but it's y2 minus y1 over x2 minus x1. Or subtract the y's over subtract the x's. Just make sure you're consistent. Graph a line given a point and a slope. You should be able to do that. If you need more help, look at it. Find equation of a line. Like this is on every single final exam that I think our math department gives. Can you write the equation of a line given a graph or given various information? Okay, this various information one is big as well. The way we did it is y equals mx plus b. For any one of these, you first need to find m, and then you need to find b. Different ways to find m or to find the slope. You can look at those problems. I would definitely do some of these problems from these sections, especially 35 through 57 right through here. Do you know how to write parallel lines and perpendicular lines? Parallel lines, if you have two parallel lines, they have the same slope. And if you have perpendicular lines, they have opposite reciprocal. Opposite means you change the sign of it. So I just put OPP and then reciprocal. And the reciprocal means you flip it, RECIP. So things to remember to make sure you review, and maybe you do a couple questions from those. But this is all just lines. It should all be review. But you are going to be responsible to make sure that you can do that section, so I would look at some of those. This was a tough section for us, piecewise functions. Going back and look at those, find the values of piecewise functions and draw sketches. Graph a piecewise function, applies piecewise functions. So I'm just going to go look at an old quiz, see if I can find one here. If I can find a question that has a piecewise function on it. Oh, here we go. So here's number 7. Is we're just going to do one problem that looks at piecewise. Well, first we'll do the evaluating before we even do the graphing. If I say find f of 0, the piecewise, there's 3 separate pieces here. I use this piece if x is greater than 0. Well, the number I'm trying to plug in, or greater than 1, sorry. The number I'm trying to plug in is 0. 0 is not greater than 1, so it doesn't go in there. 0 is not equal to 1, so it doesn't go in there. But 0 is less than 1. So therefore, if I wanted to find f of 0, I would plug that 0 right in there. 2 times 0 minus 3 is negative 3. To find f of 5, 5 is greater than 1, so the 5 would go up into this one. Negative 5 plus 3 is negative 2. And to find f of 1, it goes x does equal 1, so I plug the 1 in here. There's nowhere to plug the 1 in, so it's just 4. Just that number of 4. But how do we graph this? Now you may have to go backwards as well, where I give you the graph and you write me the equations. The key is to find the border. 1 is being used as the border. So if 1 is the border, I'm going to try to graph. Let's just try to graph this one right now. My number one strategy that I try to give you in this section is, once you find the border, is you take the border, which is 1, and plug it in there to get a starting point. So if I plug 1 in there, negative 1 plus 3 is 2. So that means when I plugged 1 in, 2 came out, which means the point 1, 2 is on the graph. So I go find 1, 2. Now it does say greater than or equal to. You can't, or greater than, doesn't say or equal to on the bottom there. So that's an open circle if you remember that. So at 1, 2, it's kind of hard to do here. I'm going to put an open circle there. But then I'm like, well, which way does this go? Well, this is for all the values x is greater than 1. So I should be graphing this thing for everything, out this direction. So I'm going to graph the line either up like this or down like this or, across. What's the line going to look like? But I'm only going to graph it over here for all the x values greater than 1. Well, how do I find it? Well, now I use the slope. The slope of this line is right here in front of the x. The slope of that line is -1 over 1 because there's nothing there. So there's really a 1 over 1 there. So I'm going to go down 1 and over 1. So if I go down 1 and to the right 1, I get a point right there. And from those 2 points, I'll now make a line. That's one of the pieces. Now remember slope. If I go down 1 and the slope is negative, I now need to go to the right 1 to keep it negative. Because a negative divided by a positive is a negative. We also talked about in this section that this line right here definitely has negative slope because it's going downhill. You always read a graph from left to right, and this is going downhill, so it has negative slope, and I want mine to have negative slope, so I feel pretty good about that line. I'm going to skip this one right now and jump to this one. So this is when x is less than 1. So now I'm going to graph that for everything on the left side of 1. I'll graph this. Same strategy though. I'll pick a different color here. I'm going to plug 1 into the equation to get a starting point. 2 times 1 is 2. 2 minus 3 is -1. So that means when I plugged in 1, I got -1. It's also an open circle because I got a phone ringing. It doesn't say or equal to as well. So that's an open circle there. But now we have to use the slope. The slope is 2. So if I go up 2 and over 1, I end up over here. But the problem is I'm not supposed to graph it over there. I'm only supposed to be graphing this on the left side, over here somewhere. I'm supposed to be, that's horrible. That's really bad. I'm only supposed to be graphing it on the left side of 1. So I can't go up 2 into the right 1. If I go up 2 into the right 1, I end up over here. Well, the same thing as going up 2 and right 1 is going down 2 and left 1. So if I go down 2 and left 1, I end up here. And then I can draw my line from there. And that definitely has positive slope. I know it looks like, hey, it's going downhill if you follow the arrow, but you always read a graph from left to right. And this green line is now going uphill. And it's supposed to have positive slope, and this line has positive slope. I feel good about that. So here, the red part is one piece. That's why it's called a piecewise function. The green one's another piece. And then every so often we have this, like if x equals 1, then it just has a number. That's always going to be a dot. So this means when x is 1, y is 4. So I'm going to go put a dot at 1, 4, and I'll make this one blue. So when x is 1, y is 4, which is like right about there. Okay, and I don't know what's going on here. I'm hitting the button somehow inadvertently. Okay, I don't even have the pen selected. So I have a dot right there. And there's that piecewise function. So I strongly suggest that you do some problems if you struggle with piecewise, both going forwards and backwards, but that's just a little quick review of piecewise functions. There's lots of scenarios that could occur. But if we go back and look at this, I mean, you have plenty of problems that you can go back and look at in the book. If you need to, this is good. If I give you the graph, can you write the piecewise function? I would suggest doing a couple of those odds, or the 31 and 33, to see if you can do those as well. Scatter plots we've been doing since the beginning of the year, so I'm not even really going to go over that. You can ask me questions about that in class if you want. But you have to be able to plug it into your calculator. This is all calculator work. And in this section, it was a line of best fit. Now, we've done this in every single section. You know, instead of a line, maybe it was a quadratic of best fit, or a logarithmic function of best fit, or a exponential function of best fit. So the process is still the same. You got to know how to use your calculator, okay, to plug the data in and be able to generate that equation and then predict information from that. Like if I give you an x, you have to be able to find the y. If I give you a y, you have to be able to find the x. So that may be something that you do. A couple problems. Go back and try to find this worksheet, this 2.2 worksheet. It's also in section 2.2 in the book as well. Or go back and look at a test and do one of those problems. I strongly suggest, I mean, it's going to be on the final exam, some sort of scatter plot. You're going to have to be able to plug that information in and do. So make sure you know how to do those. All right, we're working our way through chapter 1 and 2. Now we're into symmetry. Oh, one of my favorite things. Check for symmetry given a graph. That's just flopping it over. You should be able to do that. Can I see if it's symmetrical to the x-axis, the y-axis, or the origin? Draw symmetric tracks, and you can look at those problems in the book, but check for symmetry algebraically. See if you remember all the rules for that. So let's see, we have x-axis. Is something symmetrical to the x-axis? Is something symmetrical to the y-axis? Actually, I might have a problem on a quiz. Let me go see if I can find a problem on a quiz here that we can look at. Ooh, even and odd, that's symmetry as well. Here we go. Determine if each is symmetrical. So here's the test, or one of the versions of the test. Make sure the x-axis, the y-axis, the origin, or none. This one right here, I can tell immediately is symmetrical to the x-axis because y is being squared. So this is all tips for you that I would write down. If y is being squared, then it is symmetrical to the x-axis. And that's something. Now, something symmetrical to the x-axis is neither even nor odd because it's not even a function, if you remember that. In this one, I see x is being squared, so I think it's symmetrical to the y-axis, but it's symmetrical to nothing because x is being squared and there's other x's. And that's the same thing over here. Y needs to be squared with no other y's. So if there was another y here, this would be none as well. But x is being squared, but there are other x's, so this is none. This is not symmetrical to anything. And on the final exam, you'll also have a calculator, so you could graph that and see that it's not symmetrical to anything. This one, if you have y cubed x to the fifth, we talked about that if you plug negative x in and negative y in and end up with the complete opposite of what you started with, then it's symmetrical to either the complete same that you started with or the complete opposite of what you started with, then it's symmetrical to the origin. So this is symmetrical to the origin because if I plug in negative y, it'll end up being just negative y cubed, and if I plug in negative x, it'll be negative x to the fifth, and I'll have completely the opposite of what I started with, so it is symmetrical to the origin. Here is one that has an x squared and no other x's, so it's symmetrical to the y-axis. Now, anything symmetrical to the y-axis has a name, and it's even. So it says which of these are even up here. This one right here. Okay, anything symmetrical to the y-axis, just another name. It's like knowing vocabulary. Something symmetrical to the y-axis is even. Something symmetrical to the origin is odd. So this one is odd right here. Again, you could check these on your calculators as well. But this one, you'll see that it's hard to graph that one on your calculator. But just remember, if y is being squared and no other y's, symmetrical to the x-axis. If x is being squared and no other x's, it's symmetrical to the y-axis. If you don't see squares, and really I should give you another one, like if we had x squared equals y squared, that would be symmetrical to the origin as well. It'd be symmetrical to the x-axis, symmetrical to the y-axis, it'd be symmetrical to everything. So you have to know that if we plug in negative x and negative y, we'd end up with negative, or x squared and y squared, we'd end up with the same thing. So it's symmetrical to the origin as well. So it is possible that it's symmetrical to the origin, the x-axis and the y-axis, such as a circle is one of those things. So definitely something I would put on my review is how to check for symmetry and do I know what odd and even are. Odd is symmetrical to the origin. The way I remembered that was odd origin, and even is symmetrical to the y-axis. And we have no special name for the x-axis because it's not even a function if it's symmetrical to the x-axis. So some good things to remember there about odd and evens. All right, or symmetry, I should say. Local max and local min, increasing and decreasing. You guys did a wonderful job on that. If you want to go back and look at that test on that section, but we're always looking at x's. Is it going uphill? Is it going downhill? So the interval where it's increasing and decreasing is always x values. I don't know if I don't know if we just kind of do one right here. I'm getting lots of calls today. So if we have something that looks like this, this point right here would be a local max. This point right here would be a local min. It's increasing whenever it's going uphill. So it's going uphill right here. So the interval where it's increasing would be from negative infinity to whatever this x value is right here. So that's where it's increasing. It's also increasing from here to here. So the interval where it's increasing would be, it looks like 0 all the way out to infinity. So increasing from negative infinity to whatever that is, and from 0 to infinity, we'd write that as a union. And it's decreasing right in here. It's going downhill right through here. So this is where it's going downhill. Then the interval where it's decreasing would be in between here. So we'll say like -4 to 0 or something like that. That's when it's decreasing. So we have to know, and we're always doing x values. That's why I'm drawing these on the x-axis. They would all be parentheses because right at, let's say, -4, the function is neither increasing nor decreasing. And that's actually a max. So this would be a local max, and this would be a local min. Local just means in a small area is it at the highest it can be. Some good things to go back and look at your notes on that stuff for all the details of that, but that's just a flyby. It also has even rod, which we just covered, so we're good with that. We got even rod in here too. Yeah, and then there are some applications of those, and you can look at those too, but this is just a quick review. All right, sketch important graphs. Make sure you know all the important graphs. Let's see if we have a test question on that as well. No, nothing there. Oh, here they are. Draw rough sketches of all these parent functions. You have to know what all of those look like. Okay, so we have a parabola here. We have an SA here. We have the one-armed man there. We got the V there, and we got the crazy-looking rational function one sitting there. Okay, this is, or the boomerangs, I should say. This is our boomerang one that looked like this. And you can graph all these on your calculator to find out. So if you want to pause this and graph them all, but this is a parabola opening up, that SA. Make sure you know all the parent functions. And then you do transformations with those functions. So just to remember, if you put a number on the inside, it shifts it to the opposite of what that is. So this means go right 6. And this means go up 2, if you remember that. So I just take the parent function. So I always do the opposite of the inside. It's always the vertical shift. And the same as the outside, opposite of the inside is always the horizontal shift. So you go left or right this number, and you always go the opposite of what it says. And you always go up or down this number, and you always do exactly what it says. And then there was reflections as well. Dilations we didn't really worry about too much, but if the negative is out in front of the entire function like that, we talked about which way does that reflect that. And if you look at that graph, that's going to take that graph and shift it upside down because it's out in front of the entire function. So it flips it over the x-axis, or this is a vertical flip. So if you graph this on your calculator, this would go, there's no horizontal shift, and it goes up 3, so it's there, but it would be a parabola that's opening down because it got flipped over the x-axis at some point in time. So this is a vertical flip, and if the negative was on the inside, and it's really bad to do with an x. Oh, here's one. If there's a negative on the inside, that flips it horizontally. And you remember PDHRV as well. You should do it in that order. Some of you had some things to remember. But they do the parent function, then the dilations. There's no dilation here. So the parent function, just if I quickly did this one, parent function is the one-armed man like that. There's no dilation. Horizontal. It looks like it's going to the left 4, so now the graph would be over here. We do the reflection. The negative's on the inside, which means, or not inside, it's being applied to the x, which flips it over the y-axis. So this graph would get flipped over the y-axis. So it would end up, or reflecting over the y-axis, so it would end up looking like that after I reflect it because the negative was on the inside. That was the reflection. And then the vertical shift means go down 2. So now if I take this graph and move it down, that red graph and move it down to the final graph, would be this blue guy. But just make sure you know what everything does. You're going to have your calculator the entire time, so I'm not going to be able to tell you to graph that, but I may say, what kind of shifting is being done here. And you need to know that, it's going down 2, it's going left 4, and then it's being reflected over the y-axis because that negative is being applied to just the x, not in terms of the whole function. And that was kind of a tricky thing, but you can play with that with the PDHRV. All right, let's go back to where we were. Oops, that's not it. Trying to finish off the learning targets. graph functions by hand, graph a quadratic by completing the square and using transformations. Again, every quadratic, if it's in this form, you should know that that's a quadratic that got, or a parabola that got shifted left 3 and down 5. This is the form we want it in. And remember, the number out in front just affects the opening. So if there was like a 4 out in front, that means it would be skinnier. If there was a 1/2 out in front, it would be wider. So it would open up wider. And if there's a negative out in front, it would open down. Just those things about. So we might have to complete the square to get it in this form, because maybe originally it's not. If it starts out as y equals x squared plus 6x plus 2, and I say, where's the vertex? You're like, I don't know where the vertex is. So we'd have to put it in this form to complete the square here with this process. Or we can find the vertex, remember, by negative b over 2a. That's another magical thing that we learned. Negative b over 2a is the x value of the vertex. So I would definitely put that on my review. So right now, this is b, and the a value is the number out in front right here, which is a 1. So I know right now that it's negative 6 over 2, which is negative 3. Now that's the x value of the vertex is negative 3. So to find the y value of the vertex, I would then plug this negative 3 in for these spots. And out would come a y, and then I would have the vertex without having to complete the square. So negative b over 2a was a process to help us to do that without having to complete the square. These problems we didn't actually do in this section, but this is the level 1, level 2, level 3, and this is level 4 right here. There won't be level 4 problems on there, but there may be some level 1s, 2s, and 3s. So you got to make sure you go back and look at your notes for distance equals rate times time. We made up a box. The work problems, we did a little template of actually worked over could do alone. So actually worked over could do alone plus actually worked over could do alone equals 1 job. The mixtures, we try to do percent times amount plus percent times amount equals, I can't write, total percent times total amount. And there's some on your review that you can look at for these as well. And then the distance equals rate times time problems, we set up that box to try to do those. So looking at those as well, just to make sure you remember those formulas and be able to apply them. All right, that's everything from chapter 1 and 2. I know that was a complete flyby, but it was just supposed to get you exposed to some of the things that could be on there. You need to do the problems that you need to work on. So you do more from a test, more from past quizzes, go back and do problems out of the book. Wherever it is that you feel like you have some holes in your knowledge, that you go back and review those topics.